So thank you, Amma, for having me for this talk. And today I'm going to present about large language models are visual reasoning coordinators. It is a paper accepted by NeurIPS 2023. So if you are interested in multimodal reasoning or something like model ensemble or multi-agent collaboration, then this talk might be interesting for you. Let me go with my self-introduction first. My name is Liangyu Chen. I currently work as a research engineer at MMLab Nanyang Technological University, Singapore. Our work, COLA, is about multimodality. And beside this, I also work on the topics of human-machine interactions, like human-in-the-loop active learning. And also I work with some other topics like data efficient and trustworthy AI. So I know EMLP is happening in Singapore, and I also live in Singapore, so we can chat at EMLP. And also after this, I will be attending NeurIPS 2023. So let me know if you want to catch up, and we can chat about research and PhD opportunities. Thank you for this, because I'm looking for PhD opportunities for 2024. So to start with our talk, I want to go through vision language models with you. I think the most familiar vision language model to most of you might be GPT-4 Vision, or in short, GPT-4V. So GPT-4V is an augmented model from GPT-4, the text version, and maybe it has some visual encoder, and it can answer in text based on the prompts in both forms of images and textual instructions. So of course, GPT-V is developed upon GPT-4, like you train the GPT-4 model first, and then you apply some visual encoder up to it to form a new multimodal vision language model. And I believe the same approach applies for BARD, which is an equivalent of GPT-4V at Google. So I believe the common paradigm is to train a large language model first, and then you augment the large language model to make it a vision language model. And in the open source community, the case is also the same. Like for BLEEP2 model, what we do is to have a large language model frozen, and the image encoder and the Q-former are concatenated before the large language model, so that the vision language model can take in the image input and take advantage of the strong reasoning capabilities of large language models. So as we all know, the language, natural language, is a high-level abstraction of world knowledge. So the language models, which is trained on millions or billions, I think now trillions of tokens, is particularly strong in various reasoning tasks. And also it applies for visual reasoning, which we will touch later. So that's a common approach to train or to build a vision language model, which is to use a large language model inside. However, if we look back, like 1 year ago in 2022, at that time, the models were not trained from the pre-trained large language models. For example, the work before BLEEP2, which is BLEEP1, the first version, was trained from the scratch, and also it was trained from image text pairs only, and such pairs are usually short. So first of all, the total count of the training tokens, or you can say training embeddings, the whole training data set is not large enough. So the model might not be able to learn anything useful for reasoning. And that's the reason why the vision language models are so bad at visual reasoning. And on the other hand, the visual reasoning tasks are very, very challenging. For example, they can require some common sense knowledge, like the geography, history, language, and culture, science and technology. And this knowledge can only be learned from the textual corpus, but not the visual ones. And also we have the second type of challenging tasks, which is physical reasoning. So if you look at the example in the middle, the question is, are there any other things that are the same shape as a large green thing? So it requires several steps of reasoning to solve this question. First of all, we need to understand what the large green thing is. So it is a green sphere on the left-hand side. And then we need to infer, is there any other sphere in the image? The answer is no. So it requires at least 2 steps to answer this question. Such compositional reasoning questions are particularly hard for vision language models before they embed large language models. And also we have some questions like spatial reasoning. So these questions are about the spatial relationship between 2 objects. And beyond vision language models, we have large language models. So these language models are usually trained on billions of trillions of tokens. So they are pretty strong reasoners. For example, the GPT model that we use every day, usually they can solve multiple tasks just by demonstrating or just use user instructions without any example shown to them. And in the open source community, we also have T5 model, which is slightly different from ChatGPT. However, T5 is also a multitask model that can do various types of reasoning. It is also a strong reasoner. So naturally, we can make a strong vision reasoner out of an LLM and a VLM. So Google did this work in 2022 called Socratic models. So what Socratic models is to follow what's a so-called Socrates method. So when Socrates was teaching his students, he usually asked his students a lot of questions about the student's arguments if he if he knows the student is wrong. And the more questions Socrates asks, the more the closer student will realize he's wrong. So Socrates' method means to ask questions to get the final answer. That's also the case for the visual reasoning. So in Socrates' models proposed by Google, the vision language model will summarize the visual scene in textual formats, and then the textualized visual context will be passed to the language model to do further reasoning. For example, in this scene, the scene is captioned to be, I last washed my hands at 3:38 p.m. And then this record is appended to the input of the language model so that the language model will know what happened without seeing the event itself. And then the language model can reason on this event. And another work follows the similar approach is visual programming. So visual programming is actually the best paper of CVPR 2020. Sorry, it's 2023. CVPR 2023, but it was published in 2022. So what visual programming did is slightly different. So it starts with a large language model, and the large language model applies a neuro-symbolic approach to call the vision language model when it needs to do so. The large language model will need to decide what parameters to be passed to the vision language model. And then it calls the vision language model to do the visual reasoning. And then the large language model gets back the results and reasons beyond the vision language model's answer. So far so good. Like it looks like one LLM and one VLM is enough for visual reasoning. But naturally, we have a question like, what if we have not one, but two, or even more vision language models? This is an interesting question because two vision language models might have different abilities, and their different abilities are usually complementary. And also, the two vision language models might have different error patterns. They might succeed in different fields of visual reasoning. And also, even if they have the same ability, they might describe the visual scene differently. And to note that the language model is blind, it has to rely on the vision language model's text output to reason. And in the case of two vision language models, the question is, who should the language model listen to? Can it find the right one between the two to find the right answer? It seems that an ensemble is needed to aggregate two vision language models. And can the language model in the middle be the ensemble that we need? So with that in mind, we propose Cohere. So Cohere is a novel ensemble paradigm that replaces the conventional ensemble method with a large language model. A conventional ensemble model can be like the averaging between the two predictions by vision language model 1 and vision language model 2. Or it can also be voting. Let's say if we have 3 vision language models, then if two vision language models vote for option A, and the third vision language model voted for option B, then the answer that the ensemble will get is option A. And what we do here is slightly different, like we replace the ensemble with a language model. And we have an example to do this. So in this example question, the question is how many vehicles have headlights on? The answer is 2 because we see the train and the bus both has the headlights. And to solve this question, what Cohere did is to have 3 actions. The first action is to have the two vision language models describe the visual context. So in this particular question, the vision language model A describes it as a bus is traveling down a street with a bus. So you see, actually, it's right. It's basically right, but it's kind of a wrong sentence. But it doesn't matter. And vision language model B describes the thing as mass transportation system is the largest public transport system in the world. So what information can we get out of this? We know there is a bus, and we know there is a mass transportation system, which is what a subway is called in Singapore. And the second action we have is to let the VLMs answer the question. So to the question, how many vehicles have headlights on? The VLM A answers 1, and VLM B answers 2. So now we have all the information from both vision language models, and then the large language model can answer the question based on their captions and their plausible answers to the question. In our case, the language model answers 2, which is the right answer to the question. So as you see, we have the captions and we have the plausible answers of vision language models to the question, both in text forms, and the language model will answer based on these textual clues. To zoom in a little bit, we have an instruction prompt for the language model. So in this prompt, we have the instruction for the language model, of course, like answer the following multiple choice question by OFA and Bleep's description, and their answers to the visual question. So OFA and Bleep are two different vision language models to provide clues. And then we include the OFA and Bleep's description, which is basically the image captions. And then we include the question and the OFA and Bleep's plausible answers. We also include the choices if the question is a multiple choice question. We also have some direct answer questions. You may find more details in our appendix. So we have basically two variants of COLA. The first one is COLA FT. By FT, we mean fine-tuning. And what we do with COLA FT is to do an instruction tuning with the instruction prompts that we have given in this slide. So it's pretty straightforward. Like for the input, we have the instruction prompts. And for the output, we would have the ground truth answer to the question. And other than fine-tuning, we also have a variant called COLA 0. And COLA 0 includes two parts. The first part is zero-shot learning. So we still have the same instruction prompts, but we don't do any fine-tuning on the large language model. And we only do a zero-shot learning, like nothing other than this instruction prompts to let the large language model answer the question. And another variant of COLA 0 is in-context learning. So what we do by in-context learning is to have two or more examples of the instructions and the example answers. And then we input the real question with the same instruction prompts, but of course, no answer. And then we ask the large language model to do the inference on the third question, which is the real question that we want to ask. So you may refer to more about in-context learning in some past literatures, and is a quite commonly used paradigm in reasoning. The reason why we have in-context learning here is because zero-shot learning is usually performing bad with COLA 0. Like the language model sometimes find it hard to follow the instruction that it has to answer within the choices given. We had 7 diverse visual benchmarks for testing of the visual reasoning tasks. So for visual reasoning, for visual question answering, we have VQA V2. And for more challenging outside knowledge visual question answering, we have 2 datasets, OKVQA and AOKVQA. For compositional question answering, we have GQA for real images, and we have clever datasets for synthetic images. For visual spatial reasoning capability, we have VSR dataset. And for visual entailment, we have ESNLIV. So here are a few qualitative examples that I want to show you. The first column is an example question from outside knowledge answering, outside knowledge visual question answering, and also the second column. And the third and fourth are from ESNLIVE and I believe spatial reasoning, visual spatial reasoning datasets, respectively. And for each of the question, we would have the OFA and Bleep's caption about it, about the visual thing. And also we have the OFA and Bleep's answer for the question as well. In the choices, I have underlined the correct option. For example, for the first question, the correct answer is forehand. So as you see, both COLA 0 and COLA FT can answer the question correctly in this case. And an interesting pattern is that OFA answers this question wrong, and Bleep got it right. And for the second question, it's interesting that now OFA got it right and Bleep got it wrong. And both Cola Zero and Cola FD can answer the question right. And the third example is even more interesting. So the question is, does this image describe puppy running after a stick in grass? Actually, we cannot see any stick in this image. So among the choices, yes, maybe, no, actually we should choose maybe. So interestingly, OFA and Bleep both got it wrong. And Cola Zero got it wrong as well, but Cola FT got the right answer, maybe. So you see, actually, it can be inferred from the OFA and Bleep caption because it doesn't see a stick in any of the captions. Okay, I think you guys might be wondering, okay, this is a little bit mysterious. Is Cola really working? Like, is this bluffing, or the Cola is really working? So I did some application studies to show this. The first set of experiments is to compare Cola, which is number 8, with number 1. So number 1 is OFA only plus FLAN-T5. So FLAN-T5 is a large language model we use in our experiments. And in our experiments, the 2 vision language models we use is OFA and Bleep. So in this set of experiments, what we can see is that if we have both Bleep and OFA, then the Cola outperforms the case of OFA only. So it shows that the ensemble exists, and to have an additional model, which is Bleep, really increases the performance. And the second set of experiments is whether we should include captions. So we have number 3 experiment in which we have VLM's plausible answers only, but without captions. And again, we notice some some performance gap between the ablation and the full Cola FT. To give you guys more context, for the accuracy value, we tested on AOKVQA validation sets, and the language model is always FLAN-T5 in this set of experiments. And the third set of experiments that we get in this ablation study is that plausible answers also help language model predicts. Actually, it's more important than the captions. As you see, there is a larger gap between this set of experiments, between this set of experiments and Cola FT. And another set of experiments told us that caption labels help LLM predict. So what are caption labels? I think I need to go back a little bit. So this is the caption label, like the OFA's description and also Bleep's description. So these 2 are caption labels. And the plausible answers label is OFA's answer and Bleep's answer. So if we keep the OFA's caption here, and we change the prompt before OFA's real caption as Bleep's description, of course, it is wrong. And we want to test what happens if we really did that. So when we perturb VLM caption labels, both at fine-tuning and evaluation, we found that the performance of Cola FT drops, but not a lot. But we can still tell caption labels help LLM predicts. And the case is somehow different when we do the perturbation of answer labels. So when we perturb the vision language model answer labels, both as fine-tuning and evaluation, we found that the performance dropped even more compared to perturbation of caption labels. And we also want to know what happens if the language model can learn the correct VLM answer patterns at training, but what if they cannot apply it at inference? Then we did another set of ablation study. In number 7, what we did is to have the correct vision language model answer labels in fine-tuning so that the language model can really learn the vision language model answer patterns. And then at inference, we swap the vision language model answer labels. So the knowledge language model gets at training about the vision language model cannot be applied at inference. And this time, we also noticed some significant performance gap between this set of experiments and COLA-FT. And by that, we have proved that indeed, language model is learning from the answer patterns of vision language models, and it applies what it has learned as instruction tuning to inference. To show you more evidence, I also gave the examples of the COLA-FT's answer when the VLM answer labels are swapped. So for example, in the first question, the correct answer should be forehand, and it is the beliefs answer. And if we swap the answer label of OFA and belief, and then the language model will answer backhand. So that means the language model is always following the beliefs answer, like it trusts belief in this type of question. And we also noticed the same pattern with the second question. And there is something else that I can show about how COLA works. So in this visualization, what we do is to visualize the importance of the input prompt tokens by input gradient saliency feature attribution. And in this case, the input is the tokens before grassy, and the output should be grassy. So to get the final answer grassy, the model needs to attend to some words like grassy, like hilly, sandy, muddy, and even the word in the prompt answer. So we compared what we have observed from COLA-FT and COLA-0, and we noticed some interesting patterns. First of all, both of them attend to the really informative tokens that will help answer the final answer the final output. For example, in this example, the grassy is the final output that should be given by the transformer model. And then the model is attending to hilly, grassy, and terrain, and flat and grassy, these tokens in the input prompts. And for both COLA-FT and COLA-0, they are attending to the tokens like plausible answers and the question, like what type of terrain, and also they attend to the choices. However, we noticed something different is that COLA-0 attends also to the instructions and also the vision language models, the vision language model labels. For example, it attends to answer multiple choice question, because this is also informative for COLA-0, where it's for COLA-0, because COLA-0 didn't learn much about the intrinsic nature of the text before. So it has to take good care of the prompt that is the instruction prompt it is given. And also the in-context learner COLA-0 should also attend to the vision language models labels, because it is what it needs, because it is what it needs to get the answer right. We have tested our both COLA FT and COLA 0 on 7 diverse visual benchmarks. And among 4 of them, COLA has achieved state of the SOTA results compared to any other method before we published. Yeah. So actually, we have also tested decoder-only models because decoder-only models are more popular than encoder-decoder models. For the other experiments, we did it with the encoder-decoder model FLAN-T5. And I want to show you some ablation studies about scaling COLA. The first of them is about to have more vision language models than 2. So we have 2 settings here. The first setting is to have COLA with 3 identical models. In this case, we have 3 OFA-based models. And we notice that the delta between this best single model baseline and COLA FT is 2.78 in terms of accuracy. And if we have COLA with 3 different models, we would have the delta as 8.5. Like if we minus COLA FT, if we minus OFA-based performance from COLA FT. So that means if COLA works better if we have different models than when we have COLA with identical models. And the second question that we pursue is how many more vision language models should we have? The answer is different. It depends on whether we are using COLA FT or COLA 0. So we have tested COLA FT and the 2-shot learning version of COLA 0. And we found that the more vision language models we have, the better performance we get with COLA FT until we have 5 vision language models. And for COLA 0, it's much more challenging. Like we can have at most 3 vision language models. And after that, the performance will decrease. So this is not surprising, actually, because the model that we use, FLAN-T5, was not specifically optimized for long context. And this case can be different with long context large language models that we use today. We also tried to scale the large language model size and try to see what we will observe with different magnitudes of large language model parameters. So we have tested 4 scales. They are small base XL and XXL variants of FLAN-T5. And we noticed that COLA 0 is an emerging ability that only appears on 3 billion and 11 billion variants of FLAN-T5. This is expected because we have known that in-context learning has been an emerging ability on large language models only. However, for COLA FT, the case is different. Like even if we have small models, the COLA FT could still work. And we also try to scale the data size. And we found that when we have 1 exemplar or 1 training data, if we have 1 exemplar, then the performance can be quite bad. However, if we can have more exemplars in the in-context learning with COLA 0, the performance quickly increases as we have 1 or more than 1 exemplars. The case is interesting when we have about 5 or 10 or 100 training examples. If we have 5 to 100 examples, then the COLA FT doesn't outperform COLA 0. I guess it's because the training can be unstable when we have too few instruction tuning examples. And we also want to answer the question whether COLA FT transfer across different tasks. So we have tested 3 different tasks. AOKVQA, visual entailment, and visual spatial reasoning. And the way we test this is we first fine-tune 3 models on AOKVQA and visual entailment and visual spatial reasoning, respectively. And with that model, we inference on the other 2 data sets. Like for AOKVQA, we inference on visual entailment, and we also inference it, we use it to inference on BSR. And then we found that the inference capability outperforms the number in the brackets, which is in context 2-shot learning. So by that, what we find is that instruction tuning really improves the performance when it is compared to in-context 2-shot learning. And we know COLA-FT is generalizable across out-of-distribution tasks. And to conclude this talk, I would like to discuss one important question that you might have in mind. So now we have large multimodal models like GPT-4V that have already embedded large language models. So what can we get out of COLA today? I think it's quite straightforward because, as you see, COLA is a universal paradigm. It's actually special about visual reasoning. It's not specifically optimized for spatial reasoning, for visual reasoning. So can COLA be applicable to other domains? I think the answer is yes. For example, we can have audio, and also we can have some multiple domain experts. Like, let's say if we have 2 or more experts in law, and then the language model can consult them and decide which should it listen to. And also we have more tool learning today. Like for GPT, it can use multiple plugins, and it may use more than 1 plugin for the same task. And with COLA paradigm, the language model could decide which is the right tool or expert to learn from. Yeah, I think that's all about my talk today, and it's about some time for question and answering. Thank you.
Hi, I have a question.
Yes.
So, like in the current settings, you use the caption for both Ola and, let's say, Blip. But don't you think that the caption limits the ability? So maybe like if you can incorporate like the embeddings somehow that can improve the reading more or something like that.
I see. That's a good question. I think it's a trade-off between the caption quality and the use of embeddings, because with embeddings, of course, we can get better visual understanding, but that means you cannot apply black box large language models like GPT-4. In our example, we intentionally operate everything on the language interface, and we didn't want to do any intermediate operation on embeddings or tokens. That's the purpose of this study, but I do agree caption quality matters a lot because it provides visual clues for the large language model to predict for the visual reasoning task.
Right. And also when the number of models increases, the quality is decreased. So maybe do you think it is because of the conflict or in the captions that multiple models have?
Yeah, I think so. Like the more vision language models we have, the harder for the language model is to distinguish the patterns of vision language models. Like it has more to learn about the relationship about different reasoning agents. So it might be harder. But that's some unexamined thought, and I think we need more rigorous experiments to test this assumption.
If we don't have any other question, then I think we can end the session here.
Cool. Yeah, thank you all for your time, and thank you, Amma, for having me for this talk.
Thank you so much. It was a lovely talk. Really enjoyed.
Thank you. Bye.